is lecture 16. So we'll talk about Taylor series and Maclaurin series. Taylor and Maclaurin series. Right. So we'll try to extend some ideas from series representation. Okay. So we've done the power series as well. Okay. So let us start with an idea. We have a function. We have a function f of x, right? Having a power series representation on an interval I. See, we have done that part that we have a power series representation on an interval I, right? Because we know that there is a certain radius of convergence, and sometimes the power series do not converge to that particular sum if we are not into the interval of convergence. So let's assume that if it has a power series, the power series have an association with the interval as well. So it should have a interval of convergence as well. So let's say we have a function who has a power series on some interval of convergence, let's say on I. So we know that if you have a power series, so this power series can always be written as in this way, right?
Your voice is not coming.
Yeah.
Yes, sir.
Are you getting my voice?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So x minus a raised to power n, a is what?
Center.
Yeah. And what is Cn?
Coefficient.
Yeah,
Three.
coefficient. That's it. That's it. So you know the normal notation, right? That's how that's how we can represent the f of x in terms of series. Now, suppose we have an additional advantage, right? Suppose we have an additional advantage that let us assume that f of x is continuous and differentiable. Continuous and differentiable with all order of derivatives. Right? Sometimes you have a function which is, let's say, which is not differentiable every time. So can you give me an example of whereas a function is differentiable 2 times, but third times it is not differentiable? That means f and f dash exist, but f dash and f double dash exist, but f triple dash does not exist. Can you think of that function? Anybody? Anybody? You don't know such functions? आ रहा है दिमाग में? Or you may have a function where f dash exists but f double dash does not exist. Just think about it, okay? Just think about it for a second and try to construct an example where this may happen. Okay, anyways, so this is not our basic question. So our basic question is, let's say we have a nice enough f of x which can be so much innocent that it is everywhere continuous and you can differentiate it as many times as you want. So suppose we have this kind of f of x. So what we're gonna do, we'll differentiate both sides on the power series, right? So can we differentiate? So can we really differentiate on both sides? If yes, then why? Bolo?
Sir, because fx is differentiable.
Yeah, that's true. But why on the right hand side?
So we studied that theorem.
Sir,
Yeah.
at every x which
Yes.
is convergent, the power series is differentiable and it
Term
can be
by term
integrated.
differentiable and term by term integrable.
Integrable.
That's why we can
Yes.
do it. Okay. So that's why we can do it. Right. So since we have power series representation, Anna, only then we can do it. Okay, that's why. So I'm just leaving it. We don't need it actually. I mean, we need it just because we want to differentiate. Otherwise, we don't need to mention it separately. Okay, so just differentiate star on both sides. So what will happen? So you'll write it as f dash x on this side. So you write it as f dash x over here. So when you actually expand it, what are you gonna get? Your first term would be what? C naught. C1 x minus a1, C2 x minus a whole square, and so on up to infinity, right? That's how you
Yes, sir.
expand it. So derivative of C0 would be what? 0. And derivative of the first term would be what?
C1.
C1 plus 2C2 x minus a plus 3C3 x minus a whole square, and so on up to infinity, right? Now again, you take what? You take the second order derivative, f double dash x. Okay, so that becomes what? 2C2 plus 6C3, right? Or more precisely, 3 into 2 into C3 x minus a, right? Plus next would be what? 4 into 3 into 2 C4 x minus a whole square, plus so on up to infinity, right? That's how we're gonna do.
Yes, sir.
Yes.
Okay, is it fine? Is it
Yes,
fine?
sir.
Okay, so let's
Yes,
say
sir.
if I see these two sides are equal for every value of x, right?
Yes, sir.
Yes,
Now
Yes,
sir.
sir.
suppose if I put x is equal to a over here, what I gonna get? If I put x is equal to a over here, f
C1.
dash a c1
C1.
plus these all the terms will be what?
0.
0. So if I
0.
put at f double dash at a over here, what are you gonna get?
2C2.
2C2.
2c2. In the same way, if I put f3a, that then what are you gonna get?
3C3.
No,
C3.
3 2c3,
Okay, sir.
right? Every time you'll get the power over here. Okay, so
Yes, sir.
from here, what are you gonna get? You get that your c1 is nothing but your f dash at a. So c2 is 1 by 2 times the f double dash at a. Actually, it is 2 factorial. And similarly, from this, you can find C3 as well. And what is your C3?
F triple dash upon 3 factorial.
Yes, 3 factorial, right? And similarly, if you keep on doing like this, so your Cn would be what? F nth derivative at center upon factorial n, right? So the series representation which we used to have, this thing, right? So your star was what? Now by star, what was your star? That was f of x c naught c1, right? C1 x minus a c2 x minus a whole square plus c3 x minus a whole cube, so on up to infinity, to by star. So this star can be rewritten as fx is equal to, what about c naught? What about c naught? Can anybody tell?
Sir, f of a.
F of a. That's it. You put x is equal to a, everything will be vanished. You are left only with the c naught. So your c naught is nothing but f of a. And what was your c1? You have already done that. C1 is
F dash A.
dash A. That is your C1, right? F dash A. Okay, so we'll write it as F dash A into x minus A plus, what is your C2? F double dash A upon 2 factorial into x minus A whole square, and F triple dash A upon 3
3
factorial
factorial.
into x minus A whole cube, and so on up to infinity, right? So is it fine? So is it
Yes, sir.
fine? So what if, so
Yes, sir.
basically there is what? So we have shifted from, we have converted the coefficients of power series in terms of what? To the what? Derivatives of क्या? किसके हैं derivatives?
F
F of
x.
x.
F of
किस
x.
point पे? At x
At
is equal
A.
to A.
A.
And A is what? Center.
Center.
There.
Right? So basically you have somehow rewritten the power series in terms of what? In terms of your coefficients of power series. You have changed them into the derivatives of a function. That's it. Okay? Is it fine now? Right?
Yes, sir.
Yes,
True?
sir.
Can you see this? Is it fine now?
Yes, sir.
Okay, so now we'll define formally the Taylor series. So let f of x be a function with all order derivatives, all orders of derivatives on some interval I with an interior point A. Interior point A. Then Taylor series generated by f at x is equal to a. What we'll say? By f at x is equal to a. Always keep in mind when I'll use the terminology, I'll say that this is the Taylor series generated by f at x is equal to a, will be defined as, on the next page I'm going to define it as k runs from 0 to infinity, kth derivative at a upon kth ka factorial into x minus a raised to power k. That is something which we already done, right? F of a plus f dash a into x minus a plus f double dash a into just a minute, into x minus a whole square by factorial 2, right? Plus so on, and at some time we will reach at n as well. And just like this. Are you getting this? Is it easy?
Yes, sir.
Yes,
Yes,
sir.
sir.
That's easy. So you understood the connection of your power series with the Taylor series. Okay. So we are just determining the coefficient of the power series in terms of the derivatives of f of x. That's it. So now, what is Maclaurin series? It is pretty much easy. So just for Maclaurin series, at f, take a is equal to 0, right? That's it. That's the only difference. That means it is a particular Taylor series defined at a is equal to 0, generated by f at x is equal to 0, in other words. Okay. So it is a Taylor series generated by f at x is equal to 0. So you just replace a by 0. That's it. That will be your Maclaurin series. So I'll write it. So summation k runs from 0 to infinity, kth derivative at point 0, k factorial x raised to power k. Why x raised to power k? Because I have chosen a to be 0. Fine.
Yes, sir.
So I'll replace a to be a by 0. That's it. So let's say f0 plus f dash x plus f double dash 0 at 2 factorial x square and so on. At nth point we'll have this thing, so on up to infinity. Right? Fair enough? Okay?
Yes, sir.
Yes, sir.
Right? So we'll do few questions on this. Okay? So let's say Taylor polynomials. That is also easy. So let f be a function. Let f be a function with derivatives of order k, which is equal to 1, 2, say up to n, in some interval. In some interval containing a as an interior point. Right? Then Taylor polynomial. Then Taylor polynomial of order n. Of order n generated by f at x is equal to a is a polynomial. Right? So that polynomial is what? Pnx is equal to, we will take f plus f dash a x minus a plus f double dash a x minus a whole square upon 2 factorial plus so on nth at a n factorial x minus a up to n. So can you differentiate between that polynomial and then a series, Taylor series? Is there any difference? Can you differentiate? What is the difference?
So the series is, it is going till infinity, and the polynomial is going till n.
Yes, that's it. Polynomial will contain only finitely many terms, right? So
Yes.
sometimes it happens ki, you can define a polynomial for a function, Taylor polynomial for a function, but not for a series. Why? Because let's say some function is only differentiable for n times, and it is not differentiable for n plus 1 and higher order, right? Then we'll restrict our Taylor series to the Taylor polynomial, right? Okay, is it fine? So if some function has Taylor series, of course it will have Taylor polynomial. But if some function have Taylor polynomial, that it may or may not have a Taylor series. Is it okay? So let's say start with a very simple example. Yes, somebody want to ask something?
Sir,
Yes.
yes, sir. Switch to the previous slide, please. Done.
Okay. So let's say start with a very simple questions. So let's start with this. So this is just an example, so already present in the book, but let's say we'll discuss that part. So example is find Taylor series and Taylor polynomials generated by f of x is equal to ex at x is equal to 0. So at x is equal to 0 means what?
Maclaurin.
The value of a
Maclaurin
is
series.
0.
Yeah, you call it as a Maclaurin series. Okay.
Yes.
So now how should we evaluate it? We need the derivatives, right? So first of all, we have f of x, that is ex. And what about f of 0? That is 1.
1.
And what is f dash x? Again ex. And we need f dash 0, that is again 1. Right? So we'll keep on doing like this. We know that even your nth derivative will be equal to ex, and nth derivative at 0 will be equal to 1. So now, what is Taylor series? What is the expression for the Taylor series?
fa plus f dash a.
Yeah, fa plus f dash a, right?
Yes.
At x, f double dash
A.
2 factorial x minus a, that means x square. Okay, so f triple dash 3 factorial x minus a is 0. So something like this. So what is your f0? That is what? 1 x upon 1 x square upon 2 factorial x cube upon 3 factorial plus so on up to infinity.
Sir, expansion
Right?
है sir e की power x की.
Exactly. तो पावर सीरीज और टेलर सीरीज में फर्क ही क्या है? Can you tell me? Is there any difference?
Not really.
Not really. I mean, in the sense, if your function is nicely differentiable, then not really there is a difference. The only difference is we'll determine the coefficient in terms of its derivative. So if a function is differentiable, we can determine the coefficient, in a nice way, in a more easy way, right? So that's why. So your Taylor series at x is equal to 0 would be nothing but this thing. Okay.
Yes, sir.
Right? Is it fine? So what about the Taylor polynomial? If you want to find out the Taylor polynomial for this, if you want to find, let's say, p and x for this, anybody?
Sir, उसको बस x की power n upon n factorial से extend कर सकते हैं.
Exactly. बस यहाँ तक छोड़ देना इसको. हाँ जी. सबको समझ आया?
Yes, sir. Yes.
So that is your f of x is equal to cos x at x is equal to 0 again. Now, of course, we'll not have constant kind of derivatives again. So let's say we start it. So we have f of x, that is cos x, f dash x, that is minus sin x, f double dash x, that is minus cos x, f triple dash x, again sin x, f fourth derivative x cos x, and we'll keep on doing like this. Okay, so what happens if you take at 0, this will become 1, and this will become what? 0, and double dash will become again minus 1, and triple dash will become 0, and fourth will become 1. So you know that your derivatives are looking how they, if you take the 2nth derivative at 0, this will become minus 1 raised to power n, right? But if you take odd derivatives, they all are 0. Why? Because at this we have sign expression, so that's why they are 0. But if you take even power, then it may become minus 1 or plus 1, right? If it is divided by 2 and then you take minus 1 raised to power n, then it will behave similarly. It will behave in a similar manner. Okay, so right, so take the half of 2, so that becomes 1, that means minus 1 raised to power 1, that becomes minus 1, and here you have fourth derivative, so take the half of 4, that becomes 2, so minus 1 raised to power 2, it becomes 2, right? So that's how the derivatives are behaving at x is equal to 0. Of course, odd derivatives are 0. Why? Because At odd derivatives, we have sine, and we know that sine at x is equal to 0 will be nothing but 0. So now if we want to express the, the cos x in terms of the Taylor series, how are we going to do? Again, the expression would be same. f0 plus f dash 0 x f double dash 0 x square upon 2 factorial f triple dash 0 x cube upon 3 factorial and so on up to infinity. So it is your f0, that is what? 1 plus next
सर
is
वो
sine.
थर्ड टर्म के साथ माइनस भी आ जाएगा ना?
किसके साथ? वो तो अभी वैल्यू भरूंगा ना मैं, तब आएगा. ये तो मैंने जनरल एक्सप्रेशन लिखी है.
ओके सर.
ठीक है. So 0 times the x, third term minus x square by 2 factorial, fourth plus, right, and so on up to infinity. So this becomes what? 1 minus x square by 2 factorial plus x4 by 4 factorial. And if you take the next term, that would be x6 by 6 factorial plus and so on up to infinity. So
Yes,
this
sir.
is nothing but the expression of cos, right? So again,
Yes,
we
sir.
are getting the expression of cos x by Taylor series. Is it fine?
Yes, sir.
So have you got the idea of Taylor series? What is Taylor series?
Yes, sir.
Okay. So let's say, we can do a few questions from it, from the exercise itself. So,
Sir, please switch to the previous slide.
yes.
Done, sir.
Okay. So we have exercise 8.9 into this for the Taylor series and Maclaurin series stuff. So let's try a few questions from it. Let me go to the exercise. So question number 2. Question number 2 is, we need to determine the Taylor polynomial of order 0, 1, 2, and 3. Find Taylor polynomial of order 0, 1, 2, and 3 by f at x is equal to a. So in second question, we have f of x to be log x, log of 1 plus x, and given that our a is equal to 0. So first of all, we need derivatives. So f dash x 1 upon 1 plus x. So f dash at 0 will become 1. F double dash x minus
Minus
1
1
upon
upon
1.
1 plus x square.
Yes, f double dash at 0 minus 1. Now f triple dash
Minus 2 upon 1 plus x whole cube.
Yeah, so minus 2 minus minus plus
Yes, sir.
f triple dash at 0. So this becomes 2. Right? So now you want to find out the fp0 x. So that means you need only first term. Okay. So what is your first term? So first term is f of 0. And f of 0 is what? Log of 1 plus 0. That is 0. Now you need P1x. P1x, that means it contains two terms. What are those two terms? F dash at 0 into x, right? Because we are doing it at x is equal to 0. Otherwise, we'll take x minus a. So f0 is what? 0. F dash 0 is what? 1. So 0 plus x, it becomes x. Now, you want to find out P2x. That means this will contains three terms. F0, x time f dash 0, x square by 2 factorial time f double dash 0. So f0 is again 0. This was x. This whole thing we have already calculated x plus x square by 2 factorial into f double dash 0 is what? Minus 1. So we have our P2x is x minus x square by 2 factorial. Now, finally, we want to calculate P3x, and that is f0 plus f dash 0 x plus f double dash 0 x square by 2 factorial plus f triple dash 0 by 3 factorial x cube. Okay, so f0, we have already computed this stuff, right? P2 takka, and that was x minus x square by 2 factorial. And the next one is x cube by 3 factorial into f triple dash at 0, and that was 2. So write it 2 over here. So this becomes x minus x square by 2 plus x cube by 3. Is it fine? Yes. Tell me, is it fine?
Yes, sir.
So have you got
Yes,
it?
sir.
So that's how you can do the the rest of the parts, that how to calculate the various Taylor polynomials. Various functions are there in question number 1 to 8. So let's say try a few questions from Maclaurin series as well. This is also given to us. So let's say 1 upon 1 minus x. Question number 12. Find the Maclaurin series of this function. Function is 1 upon 1 minus x. So you need to find out the Maclaurin series. So by definition, we know that Maclaurin series is defined at x is equal to 0. So first of all, we need f0, that is 1 upon 1 minus 0, 1. Okay. Now, we need to find out f dash x, and that is what? 1 upon 1 minus x whole square. Is it okay? Is it okay?
Yes, sir.
माइनस एक और आना था ना, माइनस माइनस प्लस हो जाने थे. So f dash 0 again 1 upon minus 0 whole square 1. And what about f double dash? ये फिर माइनस माइनस प्लस 2 minus x whole cube. And f double dash 0 is 2. F triple dash x, that means 2 into 3 कितना हो जाना था? 6. Okay. And f triple dash 0 will become 6 only, and so on. Okay, so how are we going to write the Maclaurin series? Therefore, Maclaurin series of 1 upon 1 minus x is what? F of 0. So it is your f of 0, 1. F dash x plus 1 times x plus 2 times what? X square by 2 factorial plus 6 times what? X cube by 3 factorial, and so on up to infinity. Now you see these 2 will cancel. This 3 factorial will get cancelled. So 1 plus x square plus x cube plus up to infinity. So can you see what is this?
GP.
So it's a GP,
Yeah.
infinite GP.
Because you know that now your function is 1 upon 1 minus x. So that would be your GP. Okay, because the sum of the GP is there. Right? But you also know that this is not going to true every time. Okay, so this will be true only when your mod x is less than 1.
Lesser than
Otherwise, this may not be equal to this every time. Okay,